Welcome back. This is the third lecture on total unimodularity. In the previous lecture, we saw that for a problem class that we have spent some time thinking about, namely bipartite graphs, the incidence matrix is totally unimodular. And that essentially, as we see in the last lecture, gives us a different approach to showing that the LP relaxation for the maximum matching problem is integral. And also, because of the fact that basic operations like transpose or appending an identity matrix to a totally unimodular matrix preserves total unimodularity, we also essentially get this result for free that min-vertex cover, or for free by the same tools, that min-vertex cover, its LP relaxation is also integral. So this gives us another opportunity to relate using duality those two combinatorial problems without having to introduce additional combinatorial thinking as we did the first time that we encountered them. We're going to now talk about network flow and show a property of total unimodularity for this type of problem. So let's recall the basic setting. So recall that given a directed graph, the incidence matrix is now signed. When I say the incidence matrix, this is just the matrix that is nodes as rows and edges as columns, but now we need to keep track of the direction, and we do this by having a matrix that has plus and minus ones. So the incidence matrix is signed, which means it has -1, zeros, and +1. So still, of course, hope for total unimodularity. And also, remember that we had defined given a node or a set of nodes, the set of edges that point into that node or into that set of edges and into that set of nodes, and vice versa, the nodes coming out. So remember that we had also defined delta minus and delta plus defined as a function of a given node or as a function of a collection of nodes, and that basically, given these two flow conservation constraints, which is the foundation of any network flow problem, shortest path, max flow, etc. Flow conservation constraints is just saying that the fluid is incompressible. What comes in has to be what comes out. So for the max, for any node that doesn't have a supply or demand, so for max flow, for example, for any node that's not the source or the sink, the sum of edges the sum of flows summed over edges pointing into a particular node has to equal the sum of edges pointing out of that particular node. So for any v without, let's say, additional supply or demand. So for max flow, that would be any node other than S and T. Any node V that's not equal to S or T. And so max flow was our problem of maximizing the flow out of a particular node, delta plus of S, xe, subject to the flow satisfying flow conservation and also non-negativity. So flow conservation for every node not equal to S or T, and also non-negativity of the flows. Great. So our first result is that the matrix that we obtain by writing these constraints, so you can note that once I put everything onto one side, these flow constraints look like AX equals 0. A is going to have plus ones, zeros, and minus ones according to whether an edge is in delta minus or in delta plus. So fundamental result is that this flow matrix is totally unimodular. So let A be the signed matrix of a directed, the signed incidence matrix of a directed graph. And so this means that, again, just to make this explicit, the columns are indexed by the edges and the rows are indexed by the vertices, and a particular entry of A, let me call this A V1 comma E, and in that same column here will be A V2 comma E. These have to be opposite in sign to each other and equal to either plus or minus 1. So it doesn't matter, by convention you can make them either plus 1 for the pointing in or minus 1. Anyway, the constraint is AX equals 0. So that doesn't matter. But basically, let's just say that this is equal to minus 1, and this has to equal negative A V2 of E if V1 and V2 is an edge directed from V1 to V2 belongs to E, and otherwise it's 0. So that means that if I look at a particular column, this column is going to have zeros and a 1 and a minus 1. So a generic column is going to look like this. So the result is that A is totally unimodular. And I'd like to leave this as an exercise for you to do. It's not that difficult, and it's especially not that difficult if you recall the proof that we gave that the unsigned incidence matrix for a bipartite graph is totally unimodular. So I'll just say for a hint, see the proof that A for a bipartite graph is totally unimodular. And again, recall what you need to show. You need to show that for any square submatrix, its determinant is plus 1, minus 1, or 0. And so everything in all of these types of proofs, typically expansion by minors is our very good friend, and so that's what you should think about, and possibly induction. Okay, so this is so I encourage you to work this out. And as soon as we get this, we have a number of nice consequences right away. So for example, the max flow problem itself is integral. That doesn't mean that max flow chooses a single path. Of course, that doesn't have to be the case. But specifically what this says is if the capacities are integral, then the max flow solution is integral. That means that the max flow optimal solution sends an integral amount of flow on every single link. And basically the proof of this is relatively straightforward. None of these, from the point where you know that A is totally unimodular, you're not going to be surprised to learn that some LP is going to be integral. But it is nevertheless important, at least for us now, when we're getting used to this machinery, to make sure we understand exactly why. how does this property of total unimodularity directly give us integrality? And we always need some trick, and that trick could be appending an identity matrix or taking the transpose or something like that, and it will ultimately rest in showing that whatever operation is needed preserves total unimodularity. So at the core, the main machinery is that that matrix A is totally unimodular, but if we want to put an upper bound, which is the capacity, if we want to we have the non-negativity lower bound, etc., that all of this can somehow be accommodated and end up with essentially another totally unimodular matrix. Now, so we're using two things. We're using all the machinery of total unimodularity, but also we're increasingly just routinely using the machinery of linear programming, which tells us what optimal solutions look like, namely basic feasible solutions. So that is also like the key thing here that we're using. So I'll just say follows from above, which you're going to show yourselves, and also using the fact that if A is totally unimodular, then any subcollection is going to be totally unimodular, which is just from the definition. So any submatrix is totally unimodular. And of course, we can keep going. So we let's revisit max flow and min cut. So now let's this gives us an opportunity to remember again what a cut is. Recall that we've defined cuts in two different contexts. Cut can either be specified by the edges, which partition the graph with S being on one side and T being on the other, or and we did this when we were talking about arborescences, something that we're going to revisit in future lectures. A cut could be defined by a set of nodes, because a set of nodes automatically specifies a set of edges which separate that set of nodes from the rest of the graph. And so these are essentially equivalent, but there are different ways to specify. So in the context of max flow and min cut, we talked about cuts as a subset of edges. So we said that a cut is a collection of edges such that without these edges, there is no path from S to T. Again, max flow and shortest path, etc., have a specific privileged S and T nodes defined. Or equivalently, it is a partition of the nodes into W and W complement, such that S is in W and T is in W complement, and it's all the edges going from W to W complement. Okay, so now duality gave us the following relationship. If I'm formulating my max flow problem, let me just use a small vector W to denote the objective for max flow. So max of W transpose X subject to, I'm going to write A dash as the subset of my flow matrix A, where I don't have edges S and T. AX equals 0, the flow conservation. X has to be non-negative, and X has to obey my capacity constraints. And so the dual of this problem is to minimize. I have dual variables that come from these constraints and dual variables that come from my capacity constraints. So I minimize 0z plus C transpose Y subject to A dash transpose Z plus identity Y is greater than W, and Y has to be non-negative. There's no restriction on Z because like the constraints to which Z corresponds are equality constraints. Now we know, so what is the first observation here? The first observation is to show that both of these are integral. So again, we know that there's a totally unimodular matrix, but it's again important just to make sure we know exactly why. So I'll just write exercise 1. Primal and dual have not just integral values, but integral solution for any B and C integral. And as the next exercise, argue to yourself or conclude that max flow equals min cut. So what does that mean? We know that what's sitting on the left here is the max flow problem. And so we need to show that from the solution that you get on the right, the minimization, you can extract a minimum cut. So much for those for max flow. We're going to revisit that in a minute when we talk about what do all total unimodular matrices come from these incidence matrices of graphs. But before we get there, I just want to, for your use, to write down a few other characterizations of total unimodularity. So I'll write this as a theorem, and this is portmanteau theorem. The parts of it are really different. Parts of it are contributed by different authors over time. So this is just putting them all together. So it says that for a matrix, getting a little bit of abusive notation here. I'm just writing element of -1, 0, +1 to indicate. I really should write aij. I might as well write it. aij for a matrix A that has entries in -1, 0, +1. The following are equivalent. 1. A is a totally unimodular matrix. Each square submatrix of A has determinant 0 or ±1. This is our first definition of total unimodularity. This is equivalent to the following. The polytope, or polyhedron, I'm not assuming it's bounded, x such that x is non-negative and ax is less than b, has integral vertices for any integral b. And we showed this as well. This is also equivalent to saying for any integral vectors of appropriate dimension, a, b, c, and d, then the polytope obtained by upper bounding x in addition to upper bounding ax has integral vertices. Okay, so now we're going to leave this type of characterization and give something a little bit different, which should be reminiscent of bipartite, what we use for a bipartite graph. So total unimodularity is equivalent to the following property: that each collection of columns of A can be split into two parts so that the sum of the columns in one part minus the sum of the columns in the other part is a vector with entries in 0, 1, or -1. So just to draw this out, what that means is here are like the columns of my matrix. I can label these A and B in some way. Actually, there may be some, it has to hold for any subcollection of columns. So maybe there's a few that I didn't choose. Okay, so A, maybe the third one I don't select. B, A, B, 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 B. So what this says is that if I were to sum columns A, and A, and subtract columns B, 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 that means I would have a vector in +1, -1, and 0 entries. So what that means, another way to say it is, I guess I won't write this out, but it basically means that we can, is that for any support, I can find a vector that has +1s and -1s on the support, and 0s outside the support, of course, so that AX has entries in +1, -1, and 0, 1. So these are it's equivalent ways to say this. And if you think about that for a minute, and the fact that A is equal to that A is totally unimodular if and only if A transpose is totally unimodular, you can see that this is very close to the reasoning for bipartite matching. It has a lot to do with the characterizations for bipartite matching. So a fifth total unimodularity is also equivalent to the following: each non-singular square submatrix has a row with an odd number of non-zero components. I'm less, writing, I don't expect you to memorize these, but it's just an indication of how people have tried to use and take advantage of total unimodularity. Obviously, someone wrote down these results because in some cases it's much more convenient to use property 5 or property 4 than to try to prove a result about every single, about the determinant of every single submatrix. 6 is that the sum of entries in any square submatrix with an even number of rows and column sums is divisible by 4. And finally, no square submatrix of A has determinant plus or minus 2. For some of these, one direction is immediate. Like in this case, we know that if A is totally unimodular, then obviously no square submatrix has determinant plus or minus 2. It is the other direction that is interesting. So let me highlight just one in particular here, that this property you see used quite frequently. And again, this is something that we have used as well. So, but let's get back to concretely, what have we seen in terms of total unimodular matrices? It might lead us to think that all total unimodular matrices are somehow network matrices. They come from a bipartite graph, or perhaps or flow conservation constraints. And this was a question for a little while of whether it's total unimodular matrices are network matrices, or whether network matrices can be used in order to somehow characterize total unimodular matrices. And the answer is that it is possible to characterize them in this way. So I want to briefly just tell you this theorem. I think what's really useful for us is the characterization, the use when it comes towards integrality, and and perhaps that fourth definition that I mentioned in the previous list of equivalent definitions. But a main idea and motivation in combinatorial optimization, and in particular for graphs, has always been to understand when certain structures arise. So graphs that have a particular property, can we characterize them in terms of smaller graphs and building up these graphs, etc. And then the same thing carries over when we talk about matrices. So this is why I want to tell you this result. We're not going to go into proving it. So first of all, not all total unimodular matrices are network matrices, and here are two examples. I guess I'll just write these down just so you can see them. So these are 5 by 5 matrices. One, minus 1, 0, minus 1, 1, minus 1, 0, minus 1, 1, and you can check either directly or by the previous results that these are totally unimodular, that these are indeed totally unimodular. 1, 1, 1, 1, 1, 1, 2, 3, 4, 5. Oops, I guess I didn't need to that much space. Okay, so these two matrices are not network matrices. It turns out that in a very particular way that I'll explain in the next slides, these two matrices are, in a way, the only two building blocks that are important building blocks that this, in addition to a few simple operations, allow us to obtain any unimodular matrix. So before that, we need to talk about recall some basic operations that preserve total unimodularity. So some of these are clear. So if we permute rows and columns, if we just recall that the definition of a determinant as a signed multilinear form, we know that if you flip a row and a column, when you swap two adjacent rows or you swap two adjacent columns, you just change the sign of the determinant, and therefore it's not going to affect the fundamental property definition of total unimodularity. We know that a determinant of a matrix is equal to the determinant of its transpose. So what else preserves total unimodularity? So we can take the transpose. We can multiply a row or column by -1. Again, this comes from the multilinear definition of a determinant. Also, a property called pivoting preserves total unimodularity. So this is the following. Going from a matrix that looks like epsilon C B D to minus epsilon, epsilon C, epsilon B, D minus epsilon BC, where here epsilon is plus or minus 1, and B and C are vectors, so column and row vectors respectively, and then D is a matrix. So if the first epsilon CBD is a total unimodular matrix, then so is the second. What else can we do? We can add a all zero row or column, obviously, or maybe perhaps it's not that obvious, or we can add a row or column with a single non-zero which is plus or minus 1. Again, actually, either one of these I think follows pretty easily from the definition of the determinant, and in particular expansion by minors. And also we can repeat a row or a column. So these are certain operations that preserve total unimodularity. And now some slightly more complicated ones. What are we up to? 6. Property 7 is an operation that I will denote in this way. So forget about what the various definitions about circle plus, and so I'm defining this to be the matrix that makes a block diagonal matrix from A and B. This is totally, if A and B are totally unimodular, then this derived matrix is totally unimodular. Also, an operation from a matrix, I'll call this subscript 2 here, and a vector, A and A, subscript 2, B and B. I define this operation as giving me the matrix A, AB, 0, B, where A and B are vectors of appropriately either row or column vectors. And 9, that the matrix A, so again, why am I writing it this way? I'm saying if this matrix is totally unimodular and this matrix is totally unimodular, then this obtained matrix is on the right is totally unimodular. C, 0, 1. Again, all lowercase are vectors of appropriate dimension. So this is A, AB, DC, and B. Okay, so these are additional 3 properties that preserve total unimodularity. And you can try to show these by using that big list of equivalences. So this is one way where that list can be useful. Okay, so we have these operations, and these are special for the following reason. That gives us Seymour's decomposition theorem that says the following. It says that a matrix A is totally unimodular if and only if it can be built up from those 9 operations. And specifically, so if and only if A arises from the basic operations, so let me flip back here. So these basic operations like permuting rows, taking transpose, adding a row or a column with a single 1 or minus 1, repeating a row, those are all straightforward to show that preserves total unimodularity. But we also start with some basic building blocks. And the building blocks are network matrices that we get from flow conservation and these 2 matrices. And that's it. So this basically tells you that A is totally unimodular if and only if, it's almost that A is totally unimodular if and only if it's built up in this way from network matrices. It's not quite. You also need these 2 additional special building blocks, and that's why this result is so fascinating. To finish the statement, A is totally unimodular if and only if A arises from network matrices, flow conservation constraints, in other words, and the 2 5x5 matrices given a few slides ago. By applying the above operations. And I mentioned something about those, the last three operations. The last three operations can only need to be applied when let me write this down. So the above operations 1 to, what was it, 9 to 9. And in particular, we also have to specify that operations 7, 8, and 9 are applied only when matrices A and B, remember that all those, that operations 7, 8, 9 are have a matrix, have matrices A and B, and then everything else is a vector. When A and B have at least are at least of big enough size. So when A and B are large enough, and what this means is that for each one of them, number of rows plus number of columns is at least 4. And that's a story. So this tells us that essentially network flow matrices plus some operations give us all total unimodular matrices, almost, and we get a complete statement when we add in the ability to use and combine those two 5x5 matrices. So we're going to stop here, and in the next lecture we're going to move to a different characterization that we're going to use for integrality of polytopes, but now when B is fixed. So remember that for total unimodularity, we have been only focusing on this as a property of the matrix A, because the guarantees of integrality that we've gotten is that the polytope, AX less than B, or whatever the polytopes that we've talked about, are integral for every integral vector B. But perhaps we don't want that. Perhaps that's something too strong. And indeed, we're going to see that there are other things that that we can use in order to characterize integrality of polytopes. So we will pick this up in the next lecture.